Hello, everybody, and welcome to the plenary session from the Cosmic Frontier. Our format today is we're going to have two very brief talks, which are actually going to be without questions from either the audience or Zoom, but you are reminded that you can put questions in the Google Doc and we'll deal with them there. And that's to make sure that we have time for the third event, which is going to be a panel where you'll get a chance to actually interact much more directly with the Cosmic Frontier. So I think without much further ado, we're going to get started. Our first speaker is Aaron Cho from Fermilab, and he's going to tell us about the dark matter strategy from Cosmic Frontier.
Okay, great. I'm going to try to be brief and get out of the way for the panel. My main job is to kind of set the stage for the panel, but also to very briefly report the very high level strategy that we've formed from the Cosmic Frontier for snowmass. And I just want the topic of my talk is going to be the strategy for dark matter. I just want to remind you that dark matter is one of the prime targets now for new physics beyond that which we know about, and we know about it since we can see it with our eyes. We look in the sky and we think this is an image from the dark energy camera where we clearly see the Einstein ring formed by the gravitational lensing of some invisible object that we cannot see through the optical photons. So it's clearly there. We see it in various probes. We just don't know exactly what it is. And so that is our topic. Yes? I prefer not to. Okay, so this topic of dark matter is very, very wide. I'll try to speak more loudly. It spans pretty much all frontiers here at SNOWMASS, and I think this has been recognized by the community. This is a word cloud that was generated by Gordon Watts, and you can see, well, you could see if it wasn't obscured by the captions, but you can infer that you can't see the dark matter, but it's there. Okay, good. Okay, so there's a lot of excitement about this. And so our strategy, so this is a summary of the strategy. I'll just flash it here now, but we'll go back to it at the end. But as I said, dark matter poses a profound and exciting challenge to our understanding of fundamental physics. And our strategy is basically going to be to try to maximize the probability of discovery. And there's two prongs to this strategy. We're going to be delving deep to fully explore the high priority theoretical target regions, namely the WIMPs and the QCD axions. There's many projects underway. We want to continue this effort, but now we want to complement it with a parallel effort of searching wide, deploying new techniques like quantum sensors, new detector technologies in Pathfinder experiments, and also with techniques such as using new observational probes with our telescopes as well to access previously unexplored dark matter scenarios in a suite of small experiments, and also to lay the groundwork to go deep in future for these targets in future experiments. Okay, and again, as I mentioned, dark matter crosses boundaries. There's complementarity across pretty much all of the frontiers at SNOWMASS, and what we need this complementarity to really it's all including a very strong and vibrant theory program, and this is all going to be critical for not only the discovery of the dark matter, but the characterization and elucidation of what's going on in the dark sector. Okay, so this is a cartoon that was generated by several of us over the past couple of days, and of a vast multidimensional dark matter parameter space, kind of compressed down into just 2 dimensions. The dark matter mass, which now instead of just being WIMPs, we're seriously considering many, many orders of magnitude of possible dark matter masses, ranging from like 10 to the minus 21 EV all the way past M Planck to kind of primordial black hole masses. And on the vertical axis, we have just labeled this as interaction strength without being too specific about what it is, and in particular, not being quantitative about what it is either, other than to point out that we're talking about interaction strengths that range from standard model kind of interaction strengths all the way down to gravitational interactions only. So we're pretty much trying to probe all of the dynamical interaction scales that could occur in between. Okay, so I'll spend a couple of minutes going through the features of this plot before showing how we're going to attack this, this very, very nice challenge that we have before us. So I already mentioned that we have kind of this classic WIMP parameter space, which would be thermally produced at the electroweak scale. In addition to that, we have a new class of semi-thermally produced dark matter, these so-called dark portal models, in which the dark matter is produced in another sector that's weakly coupled through some messenger to the standard model. And in addition to that, we have the QCD axions that solve the strong CP problem, explain the vanishing of the neutron electric dipole moment. And then we had various models of warm dark matter, including sterile neutrinos. And in addition to that, so these are all models in which there's some interaction of there's some postulated interaction of the dark matter with the standard model, and that's why we can do these direct detection and indirect detection experiments. But we could be in another scenario in which the dark matter is just completely secluded from us. It only has gravitational interactions, which is why we can still see it in our telescopes through its interactions with the CMB and formation of galaxies and stuff. But with no interactions with the standard model, the telescopes are really our only choice for further understanding what's going on in those sectors. Okay. So where do we stand now? So we've spent a lot of great effort on searching for WIMPs and WIMP-like particles. And so this grayed out region is, again, this is just purely a cartoon, and everybody who was involved apologizes if it's not completely accurate. But we've carved deeply into the classic WIMP space, okay, as well as probing in regions nearby. And for these particle-like interactions of individual WIMPs scattering on nuclei or electrons one at a time, like billiard balls, at these higher masses, the strategy is the technique is to use sensitive detectors, calorimeters, to search for the scattering, absorption, decay, and annihilation of particle dark matter. So that's been more or less the traditional approach. And where we're going from there is with next generation experiments to, again, delve deeply into the remaining unexplored parameter space, pushing down here with next generation direct and indirect searches, as well as using the new technologies that we have, the low threshold detectors, quantum sensors and such, to push down towards lower masses and explore the portal dark matter space. Okay. And in terms of the lower mass dark matter, once you get below around 1 electron volt mass, the dark matter becomes so light that it really, the number density becomes so large that it can no longer be fermionic. The fermion degeneracy pressure would prevent the fermionic particles from clustering in galaxies at the scales that we observe. So down here, the dark matter particles have to be bosonic and form very high occupation number classical waves, just like the waves of water that splash on you at the beach. Okay, so the way to detect these classical waves of dark matter at these lower masses is to use quantum sensing techniques to try to detect the very feeble, the very weak forces that these waves exert on your sensors as they splash on them. And of course, the great success of this a few years ago, one of the experiments that I work on, the ADMX experiment, but also other experiments like the haystack experiment, have finally pushed the quantum sensing technology to a point where we reach sensitivity to comprehensively test the QCD axion model in a narrow range of parameter space. But this was a very long effort, started long before I actually joined this thing, but it was exciting to be there when it happened. And the strategy now is to continue to deploy our quantum sensing technologies to push both towards higher masses, higher frequencies, and lower masses, lower frequencies, using, again, a suite of small and eventually mid-scale experiments. And at some point, it will be necessary to hopefully to have a national axion magnet facility to host these kinds of experiments, because the magnets are a little bit beyond the capabilities of small and mid-scale experiment budgets. Okay. And then finally, we have the third category, cosmic observations, which I mentioned can probe dark matter by looking at how it's behaving in the sky, how it's clustering in the sky, and look at what its properties are, what its interactions are, without assuming that it has to interact with anything in the standard model with forces any stronger than gravity. And in addition to that, we also look in extreme astrophysical environments where dark matter can scatter or be produced. And so these provide a lot of probes that would not be otherwise possible with our ground-based or even annihilation-based searches. And so again, so it's this gray region that's currently covered, and we can push inward into the unexplored parameter space in various directions by measuring small dark matter halos that will provide us some information on what the mass or equivalently the Broglie wavelength of the dark matter could be. And looking at whether the small scale structure is suppressed, that tells us something about the dark matter self-interaction cross-section. So even if the dark matter is somewhere way down here and not touching the standard model at all, except via the formation of galaxies and halos and stuff, we can still get some information about its self-interaction that would smear out the small scale structure. We have searches for primordial black holes, either through gravitational waves or through microlensing that can push in from this direction. And of course, we have like the very energetic astrophysical objects that could be produced or serve as conversion regions for dark matter and would push in from the top. And anyway, so these cosmic probes who are using telescopes and gravitational wave detectors and such have a lot of power that has thus far not been completely utilized. And that's going to be an element of our strategy moving forward as well in motivating the next generation of observational facilities. Okay, so just again, the strategy is delve deep, search wide. And I looked it up right before this talk. DDSW does not appear to be associated with anything bad. So far we can still use it, but tell me if it's inappropriate. And just to summarize, this is kind of where we currently stand as of today. Again, just a cartoon. Apologies if the shapes aren't exactly right. These are the regions that have already been probed. And just to flash this back and forth, this is where we expect to be by the time of the next snow mass. Okay, so significantly larger areas, even logarithmic areas of this expanded parameter space, we now will hopefully have access to if we can get this program going. And I want to emphasize that even though this looks like an exclusion plot, it really is the case that there are very well-motivated models in these regions that we're probing, and a discovery really could come at any moment. And this was very nicely illustrated by the talks that we had last Tuesday from Tracy Slatyer and Risa Wexler, in which there were actually multiple dark matter candidates all discovered through a suite of experiments that would be moving forward over the next 10 to 15 years, both low mass axions, classic WIMPs, high mass WIMPs that would motivate the next 100 TeV collider as a dark matter factory in addition to being a Higgs factory. Wouldn't that be great? And also the lower mass dark matter and also a new kind of dark matter that's only gravitationally interacting. Okay, so I need to wrap this up. Again, this is the slide I showed at the very beginning. This is a profound and exciting challenge. And in addition to that, it's a tremendous opportunity for discovery that we have before us. Our strategy, again, is delve deep, continue our program to really do a comprehensive or much more comprehensive search for WIMPs and QCD axions. I think a lot of the unexplored parameter space is within reach, but then also not to put all our eggs in one basket, but search wide, develop our new techniques, deploy the quantum sensors and technologies that we're all developing or importing from neighboring fields and put them to use. There's a lot of unexplored territory, but there's also a lot of low-hanging fruit that many of us are taking advantage of right now, and then hopefully lay the groundwork for future experiments, probably mid-scale at first, to go deep on future targets if we don't find anything up here. And again, understanding the new dark sector is going to be a team effort. We're going to need everybody's help with this. So yeah, that's it. Thank you very much.
Thank you very much, Aaron. So just as a reminder, we're not taking questions for these talks, but we do encourage you to use the Google Doc and we'll try to answer them there. So we're going to go straight actually to our next talk by Marcele Santos from the University of Michigan. She's going to talk about cosmic acceleration, and that'll set us up for the panel where we will be able to interact more directly. Thanks.
Can everyone hear me okay? Thanks. All right, the magic is happening. Yeah, got it. Okay, welcome everyone, and thank you. It is a pleasure to be here presenting on behalf of really great community of, people interested in the cosmic acceleration of the universe at all scales, in the late universe and the early universe. You'll see this is a very rich program, and I'm really excited to be a part of this, and I hope to convey some of that excitement to you today. I would like to start by actually looking at the actual charge, so to say, or the vision that we have established for ourselves in this field. And as I was preparing this talk, I was like, okay, let me make sure that we are, in sync with that message. And I read this and, understand fundamental constituents of matter and energy, revealing profound connections underlying everything we see from the smallest to the largest scales in the universe. And I'm like, this is a tall order, right? But at the same time, I look at our program and I look and say, oh yeah, we are doing this, and we are doing it in a big way. I think that we are very proud to be aligned in being able to do such a rich program. It is true also that our science overall, not only in the cosmic frontier, but as a broader community, our science is it's really exciting and has been recognized as such in a big way in physics. And on top of that, I think that the cosmic frontier in particular has contributed significantly to some of that success. And moreover, we also have the ability to engage with the public in a very organic and natural way. And that is something that I think it benefits the entire community, not only the cosmic frontier, but it's something that we are very proud to be able to participate and to enable as well. So what are the fundamental questions that we are trying to address within the cosmic acceleration community? There are three big questions there. One is about the nature, the physical nature of dark energy. Is it really the cosmological constant or a new field? We don't know, and either way, the answer will be transformational. It will mean that we really are beginning to understand the fundamental nature of the least understood constituent of the universe today. Another big question that we have that we are able to address here is, did beyond the standard model degrees of freedom affect the thermal history of the universe in an appreciable way? We actually can answer this question by pursuing the Cosmic Frontier program. And I believe that this is something that will resonate with a number of our colleagues outside of the Cosmic Frontier as well. And it's a very exciting topic. In addition, going to the opposite end of the energy scale, we are able to not only test the idea of inflation, the hypothesis of inflation, but we are going to be able, with the program that we are talking about here, we are going to be able to tell what is the energy scale of inflation and what is the dynamics. I think it is absolutely amazing that I can stand in front of you here today and say we are going to achieve the level of sensitivity, precision, and infrastructure for science to address those questions. And that in part is thanks to the developments of technologies and in many other areas as well. So in the area of dark energy in particular, that's a place where the discovery that dark energy exists, meaning that the universe is accelerating today, that is something that is already happened. And in fact, that is what propelled us to get together and design a long-term plan to measure the parameters necessary to determine the physics of dark energy. And here's an example of where we are today as a result of this program, 20 years or so after that discovery, with measurements of the equational state of dark energy. And for comparison, this is the improvement level that we expect to get on those same parameters. I just pressed the wrong button. Over the time scale of the next decade. And this is also to illustrate that in this field, we are making progress in leaps. We are really not in an incremental regime, but we really, with each new generation of experiments, the advancements that we make are with one order of magnitude. Oh, thank you very much. You're a lifesaver. So I'm really excited about this. And in another level of excitement here as well is that as we achieve this level of precision, we are starting to see anomalies. We are starting to see interesting, tantalizing evidence that can be interpreted as new physics, not necessarily new physics of dark energy. It could be, for example, those beyond the standard model degrees of freedom that I referred to earlier. But in any case, getting to the bottom of understanding what these anomalies are, if they actually are a realization of new physics, this will be, a new discovery. And it's possible that it is, we could be at the edge of it at this point. Now, what are the observables that allow us to achieve all of that, right? It is actually a complex set of observables that we have, very powerful, but very complex, intertwined, and difficult sometimes to extract the information that we need. This includes cosmic expansion history, mapping distance versus recession velocity across the universe, cosmic microwave background observations, observations of the rate of growth of structure and the clustering of that structure as the universe evolves, and more recently also gravitational waves. The analysis and beyond the acquiring of the data, the level of analysis that we need to pursue in order to extract the fundamental physics out of all the other, interesting astrophysics that is on the way, it is huge. And I think that thanks to also a huge effort on the theoretical side of things, we are capable of achieve that, and we are confident that we are going to be able to pursue, this ambitious scientific program. The facilities that we have at, in our portfolio to enable this science, they are also very diverse in, the capabilities and types. So this is one area where I would say it can be a little bit different than other frontiers where there are different facilities of different types and scales and different capabilities. All of them, in some cases, working in tandem to actually maximize the science and the potential for discovery. I should have mentioned this earlier, that some of these plots, many of them, the most powerful ones, involve combination of data from multiple facilities. So what you're seeing here are facilities that are operating like right now, like DESI, the spectroscopic instrument in Kitt Peak, Arizona. A facility that we are commissioning right now. I have a graduate student who's not in this rendition, but has been living in Chile for at least half a year now, working on that. We put in the, and we have CMBS4, where we have been planning the construction and working towards that, and the gravitational wave observatories, which we have partnered in different ways so far in order to be able also to take advantage of the new ways in which we can observe the universe. It's another thing that I probably would like to highlight, that we are, I think, very dynamic in really not only developing new techniques within the scope of the technologies that we already have domain on, but also incorporating via partnerships with others as necessary to learn more about dark energy and cosmic acceleration. So what is the path forward? I hope that I was able to convey that this program was envisioned in the last NOMAS 10 years ago. This program is thriving. It is happening right now with some experiments producing science, new results and papers every day, and others being built, being commissioned, being planned. It is really, really amazing to be able to be a part of it. Now, going forward, what is the path? And this is a series of slides that are my equivalent of the cartoons that Aaron showed for dark matter, trying to illustrate that. So I'll take one of the minutes I don't have anymore to try to walk you through this, and then this will wrap up quickly after that. Okay. So I said that we have 3 questions, and we try to more or less match them in here, where inflation is here. So if you think of the traditional simplest predictions from the simplest model of inflation, what you would get? What will be those predictions? That there is a non-zero ratio between scalar and tensor modes in the very early universe that would live and imprint in the B modes of the cosmic microwave background. So these are measurements that are being pursued, and the number that you see here indicates the level of sensitivity that this experiment here is going to set up. So these are experiments that are the current generation of experiments, okay? So the other parameter, which comes also from another prediction from inflation, is that in that simplest model, inflation would be, the spectrum would be, would have no, would be a Gaussian fluctuations spectrum. So if there are non-Gaussianities, and this parameter indicates that, that would mean that you're not only learning that there is inflation at some energy scale R given by R, but also you're learning something about the physics of that, inflaton field, so to say. And here it has to do with features also in the primordial power spectrum deviating from scale invariant. So it is absolutely amazing that it's not only about detecting yes and no, it is actually achieving a point of where we actually can understand what is going on, the energy scale and the dynamics there. Here is, this parameter refers to the presence or not of extra degrees of freedom in that thermal history. This one is the one that's closest to my heart, refers to our ability to measure that parameter W of the equation of state of dark energy with 1% precision. The number here corresponds to what is the redshift out to which we can measure this with a precision of 1%. And the current generation of experiments that we are, I showed you one example earlier today, reaches about redshift 0.9. And finally here, there's gravitational waves, which may contribute here, but in this scenario, I am showing gravitational waves, the amplitude of the stochastic background of gravitational waves, which is another prediction that we expect to have, for example, from inflation, from everything in the early universe, and the level of sensitivity that the current generation of gravitational wave detectors can achieve. This, if we are able to make a detection here, this will be absolutely spectacular in many, many ways that I will let our colleagues in the panel talk about, because otherwise I'm going to be kicked out of the stage. Now, let me go then to the next decade, right? So I told you where we are. This is where we are going. So in this decade, starting tomorrow, what we'll be doing is pushing on all of these, variables here substantially so that we can cross the scientific thresholds that we have identified here for discovery or to exclude significant parts of the parameter space for these models. And in particular, I would like to highlight that our main priority here is to finish the construction of the CMBS4 project so that we can really accomplish and achieve this science here. The other new project that we envision later in the decade is a stage 5 spectroscopic facility, something that would be to DESI, the current world-class spectroscopic facility that we have. It will be to DESI similar to what LSST is to DES, another order of magnitude of number of spectra and the ability to do this science. Now, I know that that most of the time we are talking about a decade here when we talk about snow mass. In this case, we decided to take the assignment a little bit further and think about the next decade, think about the context of preparing so that when we are here in 2032 talking to you at the next snow mass, that we are ready to take advantage of the new technologies that will be available there. And so we have a pathways as well designed for that. So I will stop here. I'll leave this last slide here. This is our version of the strategy slide that you saw earlier for dark matter. I would like to say that this exercise being here this week has been wonderful. I think we came together even more as a community, and I'm really excited to be a part of this. And I started to realize connections that even for me being in the field were not so clear, and this would be wonderful. And I think that there are also opportunities for people who are in other frontiers to be as well even more excited, not only about the level of discoveries, but also about the possibilities of benefits to their own frontier, their own science interests based on the scope and the discovery power of this field. It is really amazing. So we identified 4 specific areas where we have strong consensus within a cosmic frontier that we want to communicate, and we want perhaps to use as a starting point to engage with the panel. And that includes carrying out, at to its full potential, the analysis of the experiments that we built, complete the construction of the CMBS4, which is ongoing, and roadmap the next project, the next spectroscopic stage 5 project, and create pathfinders for engaging with new opportunities in gravitational waves, and also other new experiments in the 20 years time scale. Thank you.
Thank you, Marcele. And remember, put your questions under the Google Doc. We will take a look at it. Now I would like to ask our panelists to come up to the stage. No, just the list. So Shonda, could you quickly unmute and do a sound test for us?
Testing, 1, 2, 3.
Perfect, first time. All right, thank you. Thank you very much. We've got a great panel here. It represents, as you can see, it's a lot, but it represents a really broad group of scientific interests that span the cosmic frontier. I'm going to ask everyone to just go down the row and very briefly introduce themselves so that the audience knows who we've got. Please start, Andrew.
Does this work? I guess it does. So I'm Andrew Sonnenschein. I'm a scientist at Fermilab and the project director for the next generation of ADMX, ADMX extended frequency range, a search for axions.
Hi, I'm Kefan. I'm assistant professor in physics department at University of Wisconsin-Madison. I am a theorist, also analyzing data of the cosmic particles, so specifically high-energy neutrinos, gamma rays, and cosmic rays.
Hi, John Carlstrom. I'm at the University of Chicago with a joint position at Argonne National Labs, and I work in the cosmic microwave background, and I'm the project scientist for CMBS4.
So I'm Jeff Newman. I'm a professor of physics and astronomy at the University of Pittsburgh. I'm an observational cosmologist using large survey data. I'm a member of PIT-PAC, the DESI collaboration, and the LSST Dark Energy Science collaboration.
I'm Stefan Ballmer. I'm professor of physics at Syracuse University. I'm with the LIGO collaboration for the last 20 years, and I'm the instrument science coordinator for the next generation project, Cosmic Explorer.
Hi, does this work? Yes. Maria Elena Monzani. I'm a lead scientist at SLAC. I'm the deputy operations manager for the LAC Zeppelin dark matter experiment, and I work also in Fermi Lab for science operation.
Hi, I'm Marilena Laverty. I'm a professor of physics at the University of Washington. I'm a theoretical physicist working in cosmology and astrophysical probes of fundamental physics. I am also involved with the CMBS4 experiment.
And Chanda, please go ahead.
Hi, I'm Chandra Prescott-Weinstein. I'm apparently the biggest person on the panel today. I'm an assistant professor of physics and astronomy and core faculty in women's and gender studies at the University of New Hampshire. And I'm in the context of SNOMAS, I'm a topical convener for Cosmic Frontier Topic 3, Dark Matter Cosmic Probes. And I'm primarily a theoretical physicist, but I also do observational high energy astrophysics and a little bit of optical too.
Thank you very much, everybody. So to get things started, we have one question that we asked all the panelists to think about, and we're going to hear their thoughts about. The question is, how do you see the cosmic frontier contributing to our understanding of fundamental physics in the near future? And again, for this, we're just going to go down the row and ask everybody to answer, and then we're going to open it up to questions to the audience and from Zoom land.
Okay, thank you. So I'm going to talk about what I think is the coming golden age for dark matter direct detection. So this is something that was already covered very well by Aaron in detail, and I'm going to give a little bit more personal and historical version of the last 3 decades, but in 3 minutes, maybe a few more than 3 minutes. So I remember back in the 1990s when I was one of the early generation of CDMS graduate students, we were having a lot of fun inventing new ways to detect WIMPs. If you went to a conference back then, they were full of new ideas, just all kinds of things, many of which frankly didn't pan out. But it was a great time to be a professor at a university with a few graduate students in the basement tinkering. We didn't quite get the expected sensitivity during that decade. But by the next decade, that was the decade of what was called by the DOE down selections. So the field began to narrow and focus on a smaller number of techniques that were really well demonstrated, particularly the liquid noble gases and liquid xenon, which came out as the leading technology by the end of the decade, was clearly established as the way to look for WIMPs. And you've seen how that's developed with the triumphant results that came out recently with the LZ experiment. So that was wonderful. There was a little bit less going on for the basement tinkerers because the field had narrowed, the technologies had been chosen. And so, for some people it was less exciting, but perhaps more important for the field, the program was very narrowly focused on WIMPs. We didn't make much progress on axion detection during that decade. And really there wasn't a lot going on looking for other types of particles, such as the very light dark matter that is of interest now. So then, switching, coming to the most recent sort of 5 to 10 period, now it seems that we have everything, because in the last decade, there's been an explosion of interest in new techniques for dark matter detection, some of them based on new quantum sensing ideas, as Aaron mentioned, but others that are just legitimately new concepts for dark matter detection. And these are still in the 1990s stage. So it's a wonderful time to be poking around in your lab, trying out completely new ideas, things you can do with a graduate student or two. And we know based on history that not all of these will work out. I expect that the field will develop in more or less the same way, and that over the next decade or two, we'll fully explore the QCD axion parameter space, for example. So I see this as the best of all possible times to be involved in searches for dark matter. We have everything. You can have your cake and eat it too. Great for tinkerers, great for DOE project managers. It's gonna be amazing.
Okay, so I'll start by saying that this is a very interesting time because since the last snow mass in 2013, several major discoveries happened. This includes, but not limited to, the discovery of the high energy neutrinos by the IceCube Observatory, the detection of gravitational waves by LIGO, and as well as the observation of photons above 100 TeV by air shower gamma detectors, including the Hawk Observatory. So this so-called messengers has attracted lots of attention and interest from the astronomical community, and the multi-messenger astrophysics was prioritized by the Astrophysics Decadal Survey in 2022. So I think that offers a nice opportunity for us here in this audience because these astroparticles and messengers offer perfect place to study particle physics. And I think this is a great time to start to think about multi-messenger particle physics as well. And very specifically, I think these messengers and astroparticles offer advances in fundamental physics in near term in 3 different areas. The first is, I think the cosmic probes offers you an independent way to explore the physics that's studied in other frontiers. For example, the IceCube upgrade project, which is fully funded and start to run in 2026, is going to provide precise measurement of the neutrino oscillation, the neutrino masses and mixing angles. And this is a complementary observation comparing to the long baseline experiments such as DUNE. And secondly, the astroparticles, because of their high energy, they offer you a window to study the particle physics that you can otherwise not access through the accelerator facilities. And for example, there's already an interesting hint of a muon access in the cosmic ray data observed by the Auger Observatory that suggests that a simple extrapolation of the physics calibrated at LHC energy to 10 to the 18 electron volts does not explain the data. And maybe some beyond standard model physics might need it to explain this data. And finally, I think these astroparticles provide a natural candidate to the they are natural candidate of the annihilation and decay products of the heavy dark matter particles. So by looking at bumps or lines in their spectrum, looking at their distribution in the sky, you might be able to capture the fingerprints of these heavy dark matter particles. So I think that's where the astroparticles specifically can contribute in the very near long term.
Right. Well, Andrew inspired me to give my life story in my field. I want to say that I work in the cosmic microwave background, and it's been fantastic. I hope you all agree that just the results that have come out of the cosmic microwave background in the last few decades have been spectacular, and it's been, an absolute privilege to be part of that and really fun. But what I'm really excited about for the next few years is that we have taken all these groups and come together to build this thing we call CMB S4, Stage 4 CMB project. And we are going to hopefully detect primordial gravitational waves from inflation. And that's just amazing. We're talking about energy scales of 10 to the 16 GeV, quantized gravity, just a spectacular science case. We're also going to be able to measure with high precision any sign of red-like particles from the early universe or phase transitions through this parameter we call NF. But basically, we can measure the presence of particles regardless of their cross-section to a large part. We measure that essentially their impact on the energy density of the universe, and we can get at their dynamics. And we're all going to be able to do this because we've come together, we're working with the national labs, and just having a precision that is just unthinkable. So I think we've had an amazing run with their cosmic microwave background, but the best is really yet to come, and really looking forward to that.
So I'm excited by the data sets that we're going to have now and soon from DESI and the Rubin Observatory Legacy Survey of Space and Time, which are really going to allow us to take the sort of precision constraints we get from the cosmic microwave background on many, many aspects of the universe and start to get those precision constraints on dark energy as well. And hopefully figure out what's going on there, simultaneously get tests of gravity, many other constraints on the universe, and build the legacy that we hope to build on with a stage 5 facility that would allow us to explore inflation from the ground at optical wavelengths.
Okay. Thinking about the fundamental physics contribution from a gravitational wave observatory point of view, let me first start in the past. And I'm going to ignore the discovery direct of gravitational waves because, that's sort of too obvious. But I think that the biggest one in the past was actually just the speed of gravity measurement that from a single observation actually ruled out lots of models for alternative models for trying to explain dark energy. Going into the future, I think in the next couple of years, probably the most exciting thing is going to be a completely independent measurement of cosmic acceleration. That's going to come from the gravitational sector. But then also starting to look further into the future with the next generation facility, we're going to have the ability to actually observe black hole mergers far back in the universe before there were any stars. In other words, we would have to be primordial black holes. So we're starting to cover the dark ages from that point of view at a stellar size scale, something that we can't do any other way. And then ultimately, of course, gravitational waves are the messenger if you're interested in inflationary physics, and having directly access to them here on Earth is just a tantalizing future ahead of us.
Hello? Is it loud enough? Sorry. I was saying I went to undergrad in the golden age of standard model, and I was taught that, particle physics was almost complete. There would be like a couple of kinks to work out, but we were done. I should not have a career in particle physics. By the time I got to grad school, it was very evident that the standard model described 5% or less of the total matter energy content of the universe. And that was very exciting. I call that job security. I think that the big, the big news on the last, I've been looking for WIMPs for the last 15 years, on and off, not full time, not finding anything. And we made a 10 order of magnitude improvement in sensitivity, but it's still a very, very small part of the parameter space. And since the last NOMAS, we've started looking in other places, and we all show the plot the team made at the last NOMAS, and we're looking at other places. And this is very exciting. We have action experiments, we have dark sector experiments that are being designed. So I'm hoping in the next decade, we will be able to look for things other than the standard WIMP, and we will, carve out spaces in the large parameter that, Aaron just showed.
Okay, I am excited about the cosmic frontier in the near future, contributing to fundamental physics in a handful of ways. And these are the fact that our observations of the universe have the potential to address questions and tell us about information at the highest energy scales. Our searches for primordial gravitational waves can tell us about symmetries that could be present in quantum gravity. Our searches for primordial gravitational waves and primordial non-Gaussianity can tell us about the presence of degrees of freedom and interactions at the highest energy scales that we really hope to see, and even provide some information about the quantum origin of structure in our universe. Coming down to other probes, we also, a second thing that I'm particularly excited about beyond those things related to inflation and the highest energy scales is the fact that our experiments in the near term are really probing the energy contents of the universe during the hot thermal phase of the Big Bang with extraordinary precision. So we currently know the energy density in relativistic species in the early universe to something like 4%. And one can make firm theoretical predictions for what the energy density should be in any light degree of freedom that came into thermal equilibrium at early times. And so since we can do these blunt sort of gravity experiments, we're really sensitive to interactions and stuff at a very, it's very hard to hide new physics in this way. So I look forward to hopefully detecting new particles that are present in the early universe, or learning that for some reason there doesn't seem to be anything else that is present in the early universe at energy scales, quite high above the standard model.
And Chanda, if you could please answer the question.
Yeah, it was so great hearing everybody else's answers. So as I mentioned before, I'm a topical convener for CF3 dark matter cosmic probe. So I'm going to particularly answer this question from that perspective. And also I'm just going to remind the audience that unlike the rest of the panelists, I can't see your faces. So please bear with me. So Aaron said in his talk just a little bit ago that dark matter offers a profound and exciting challenge to fundamental physics. And so I think there are ways in which it's very obvious why the cosmic frontier is so exciting, because of this challenge that dark matter and dark energy, although my focus is on dark matter, presents to fundamental physics. And so importantly, galactic and extragalactic physics is how we first identified the dark matter problem. And it continues to be one of the main sources of information about how exactly dark matter is, even while we're still not really sure what it is. And we're supported with fantastic terrestrial ground-based facilities that have successfully done the hard and important work of telling us what dark matter isn't. So I want to emphasize that from my point of view, the work that we are doing in cosmic probes of dark matter is synergistic and complementary to terrestrial experiments. I don't see a competition here. I think that they go hand in hand and together are important. And while there are scenarios where dark matter detection will ultimately only happen via cosmic and astrophysical probes, there are many plausible scenarios where terrestrial and cosmic probes are going to successfully work together to narrow down dark matter's distinct properties. So I think one of the things that we should be clear about is that we're confident that dark matter is out there and that the detection event has in fact already happened. What we don't know is what its unique Lagrangian terms are. What are those unique characteristics? So I think at this stage, we're talking about an incredible forthcoming decade of dark matter, where we are developing the capacity and potentially are already in a position to uniquely identify the characteristics of dark matter. And it may be completely impossible to do this without contributions from observations beyond the atmosphere. So I think cosmic probes have a really important role to play. And importantly, we not only complement terrestrial searches, we also inform terrestrial searches and potentially can probe unique dark matter space. So this includes checking specific signals from dark matter distributions in galaxies, clustering of dark matter halos, also looking at extreme environments. There was a great comment earlier today from Yor Carandel, who mentioned that nature accelerates particles to scales that we cannot even fathom, and that may have implications for dark matter. And so looking out into space continues to be really important. It's also not clear that a terrestrial direct detection event will give us all of the information that we need, because looking at cosmic probes still tells us how dark matter behaves dynamically on large scales that are simply not accessible to us here on Earth. And the thing that we may see in the lab may be a subcomponent. So this was a comment that was made by someone earlier this week. Unfortunately, I don't know who exactly made the comment, but I just want to say someone is out there in the audience. And so this means facilities like CMB S4, Vera C. Rubin Observatory, and future facilities that people are talking about all have a potentially major role to play and understanding the particle physics details of what dark matter is. So these are particle physics experiments. I want to add also that Cosmic Frontier sets an excellent example of interdisciplinarity, pulling people together from across particle physics and astronomy, including theorists, simulators, observers, and experimentalists. We are highly collaborative and innovating new ways of working together in big teams with large data sets and big ideas together. And this is an exciting example of the form that 21st century science has taken, bringing diverse demographics together. So I invite people to look at our facilitators in CF3 and the teams who have worked on the white papers. We have work to do always, but we are demographically diverse, reflecting an important growth area for particle physics in particular, in a direction where both DOE and NSF and the Office of Science and OSTP have established clear priorities to enable science. So I just want to remind people, for people who missed the panel earlier today, Regina Caputo had a great comment. The power of the cosmic frontier is that we're seeing particles where they are being accelerated. We're seeing dark matter where it is on distant scales. We simply can't reproduce here on Earth. And so we're a key part of the mission to delve deep into space and search wide across all 4 space-time dimensions. Thank you.
Thank you very much, panel. So what we'd like to do now is open this up to the audience. If you have a question you'd like to hear the panel discuss, also if you're on Zoom, please raise your hand and we'd be happy to see what we can say about it. You got a question, Michael?
So I think what I want to ask resonates a little with what Chanda just said. The question that was posed to the panel is, how do the cosmic probes help us in fundamental physics? But there's another aspect to these cosmic probes that I'd like to ask you about. The part that some people call grubby astronomy, but I think rather is a fascinating kind of science, but in its own right. We have to cross boundaries to do these probes. We have to understand galactic evolution and diversity better to beat down the errors in large-scale structure. We have to understand pulsars to do indirect detection. How do you think about this requirement to become a professional astronomer? How do you educate your students to cross that boundary? And maybe also, how do we educate the DOE that we're allowed to cross that boundary because that's where the science is?
That actually resonates a lot for me because coming from a field that was, fundamental physics on the ground, finding gravitational waves, we now find ourselves in an area where we can do astronomy and we can do fundamental physics, accessing the early universe in the near future. So I think it's key that we keep a broad mind of neighboring fields, other things that we can do, find overlap. I attended the lunch discussion today about the Cosmic Frontier funding currently. And I found it very interesting what the DOE funds right now has a very strategic goals, but almost all of them somehow overlap with gravitational waves. But gravitational waves is explicitly not on there. So that's something we need to be aware of, that these areas change over time, and we need to be flexible enough to decide and pursue the science that we think we want to do. That's ultimately what we need to focus on, what can be done here.
Yeah, I think that's a very interesting question. Astrophysics and cosmic probe definitely tightly linked to each other, especially in several cases. I'll give you an example. So as you just mentioned, the pulsars are believed to be dominant contributor to this interesting electron-positron axis that Pamela detected and confirmed by AMSO2. But lately there is an interesting observation by Hawk above 20 TeV. Hawk sees an interesting extended gamma emission surrounding this Gaminga pulsar, which believed to be the major dominant contributor to this positron axis. And that observation suggests that the previous understanding about the diffusion of these electron positrons near the vicinity of pulsar might be wrong. And these electron positrons might not easily go to the Earth to explaining this the solar neighborhood access. And therefore, all the native scenarios like dark matter contribution needs to be there. So I think this is a perfect example that you need to understand astrophysics to do particle physics with cosmic probes. And I think they are complementary. There are many interesting multi-messenger astrophysics programs already there. So it's a bit like a gift that's complementary for us to use those information to do particle physics.
Chanda, I see you've got your hand up.
Yeah, thank you. So this is a great question and something that I've been thinking about a lot actually from the opposite end, which is that I'm realizing that the students that I'm training in my research group don't actually understand that not everybody speaks both languages because we uniquely work at that intersection. And there aren't necessarily a lot of opportunities for people to do training in that way of thinking. I think one thing that's really clear is that we need to have the resources that allow people to take the time to cross that boundary. And in fact, we need the resources to encourage people to do that. And so I see a funding need there to encourage people to build collaborations with each other that allow them to bring in people who are non-expert. I've benefited from an NSF EPSCoR grant, for example, that has allowed me to go train with a group that was doing things that I wanted to learn about. And I see that as a fantastic model that we should be crossing those boundaries and going and learning from each other. And so I think that there's a real role for agencies to play and for those of us who are advocating. And that does mean that we may have to rethink how we bureaucratically organize ourselves, because I think that the traditional organizational strategies that we have are not working for us in terms of ensuring that people are having those conversations with each other and don't feel like it's a threat to their funding or their research success to cross those traditional boundaries.
I don't think it's always necessary for people to cross those boundaries. In DESI, we have very, very successful examples of people coming from the particle physics side who made fundamental contributions to the instrument. It's really benefited from the expertise of people who have worked on large experiments before. We also, I was trained as an astronomer. And my expertise in understanding galaxy populations and how to select the best targets for DESI has been beneficial to the project as well. And the field thrives when we can take advantage of those areas of expertise. But I've also seen in the LSST dark energy science collaboration examples of people who came in from the intensity frontier and over time trained themselves in the astronomy, and it involved becoming very involved in the collaboration at every level, taking on low-level tasks to leadership of simulations. And now they're quite expert in a variety of areas of the experiment, going beyond the hardware. And so we benefit from welcoming people in, letting them do what they do best, and benefiting from a wide variety of expertise.
Very good, thanks. It looks like we've also got a question on Zoom. Udai, would you like to unmute and ask your question?
Yeah, thanks. So I think it's very relevant to the previous discussion. So many of us are branching out to study using planetary science to study fundamental physics. And also there's a lot of opportunity that were mentioned that use space mission to study dark matter, neutrinos, and other high energy particles. So I wonder if we could create a common or shared home for all these subjects, because they are really correlated. And also related to what Chanda was saying, that it's actually hard to get support for these subjects because it's new and also it's cross boundaries. So I wonder what are the opportunities we can pursue for this kind of funding for especially young people, because we don't have our research group or grant yet. So it's actually very risky for us to explore new idea or new research directions. Nonetheless, I hope we can learn from the panel that if there are like new opportunities that allow us to do this with a reduced risk. Thank you.
Yeah, we don't have speakers.
So I think the gist of the question was, how do young people get involved and take advantage of the new opportunities that the Cosmic Frontier research offers to them? And apologies if I'm paraphrasing that incorrectly, since that's more succinct.
So I'd like to point any people interested in joining the Cosmic Frontier. So the LSST Dark Energy Science Collaboration, every year, every time they have a collaboration meeting, holds a dark energy school with lectures on selected topics intended to help people understand that data, but they're very useful for anyone getting into survey cosmology. And the lectures are available online. They're on YouTube. The materials are online. So if you search for the LSST Dark Energy School, you'll find a lot of resources intended to help people make those transitions.
Yeah, I would add on the CMB, we have similar schools. We actually have an instrumentation school this summer, although it's hard to have all that many people participate in a hands-on school. But I would also encourage people to go to the open collaboration meetings and join working groups. They're completely free and they're open. And I think you would find the climate very inviting.
I can also add from the Cosmic Explorer point of view, we recently formed a Cosmic Explorer Consortium, which is also completely open. So anybody who's interested in next generation gravitational wave is more than welcome to join there. It's a email list, periodic meetings, so that's also available.
So can I quickly, maybe I should rephrase a little bit my question. So I was more saying that kind of like the new study, for example, connection to the planetary science, like the solar system study, or space missions, like a next generation gravitational wave, but for example, in the space. So these opportunities were not included in the previous big collaboration, but are very exciting and can bring different research, for example, from NASA, from DOE, or from NSF, for example, from the quantum sensor point of view. So I'm wondering, what are the new opportunities that we can explore to further help us do this new project, and not just the like the opportunity from the big collaboration? Thanks.
Ellen, if
Yeah,
you want to give your thought first, I think.
That's what I was about to say. So I think that what's unique about the Cosmic Frontier is that there is discovery space at $1 billion scale instead of the $1 billion. I don't think that's very common in our field, and it would be like a great place to get involved. I don't know what the funding details are there, but we have this dark matter new initiatives that is looking precisely at that. And I think that the barrier there for showing up with a great idea and saying, here is how you go after this specific model, here is how to build the experiment, the barrier is quite low compared, to building the LHC. So I would point people in this direction. Is this what you were asking?
Yeah, thanks. Yeah, I think so. Yeah, thanks. Sorry, I didn't say it very clearly at the first time. Yeah, thanks.
And Chanda?
I think it's most of what I was going to say has been covered. So I will just add that I think, again, that part of the question that's being asked here is, how do we ensure that our structures are flexible enough that as the science changes direction, that our structures can go with those scientific directions, as opposed to being constrained by bureaucratic structures or structures that were put in place for older ways of thinking. And so I think that's a big challenge that we face right now. And I think part of what's exciting about SNOMAS and the leadership that I see going on in the Cosmic Frontier across all topics is that people are thinking very actively about this. And I hope that it's reflected in the final document that we see this fall.
Thank you. Thanks.
Wonderful. Do we have another question from the audience?
We do hear from other frontiers a lot about international cooperation. So how do you see importance of international cooperation, both US being involved in experiments abroad and vice versa in astrophysics?
Sorry, Dimitri, I couldn't hear that actually. It was too soft, and I'm guessing that they couldn't either.
Like that? Is it